Okay. And our speaker for tonight is Christopher Kochanek, Professor of Astronomy at Ohio State University. In 2020, he was awarded the Diane Hyman Prize for Astrophysics by the American Astronomical Society and the American Institute of Physics, and shared the American Astronomical Society's Beatrice M. Tinsley Prize with Professor Chris Stanek for their work on ASAS-SN. And Professor
good t-shirt.
Stanek's topic, old supernovae do not go gentle into that night.
Right. Now,
I can't get that. Old supernovae do not go gentle into that good night. I must have practiced that 50 times.
Where did you get the t-shirt?
Chris did.
Chris gave it to
Because
us.
I've been working with it since 2014 or whatever.
So ASAS-SN is our all-sky automated survey for supernovae is our project where we basically take a picture of the entire night sky, dark sky, every night, looking for transients and other things. We get to about, these days, about 18th magnitude on a good night. So some 10,000 times plus fainter.
Yeah.
I'm not going to talk about that project here, except I have, for this group, a technical appendix at the end, which those of you who are into magnitudes might find interesting. But the telescope we're talking about today are not the ASAS-SN telescopes, which are 14-centimeter aperture. They're really just 400-millimeter Nikon telephoto lenses, but that thing. So that is the large binocular telescope. Each of those mirrors is 8.5 meters. Anyone want to guess what a night of time on the LBT costs?
1 million.
No. $1 million. So HST Hubble is getting close to that. But you have to go into space to spend that much money. But it's more than that. So it's about $50,000 a night to operate the telescope. And so the data I'm talking about today, it comes from this thing. And the instruments we're using are actually the ones you can see there, sort of. They're the prime focus cameras. And so basically the data we're taking is, we're basically using an 8-meter to take pictures of all of your favorite astrophotography targets. M101, the whirlpool, okay? And finding something you can do with science. We must have the deepest existing image of many of these galaxies, because I believe on something like M81, our total integration time on M81 is like over a day on an 8-meter. Okay? But what we're really interested in is a time domain question, is we're interested in changes. And the story we're talking about today is how things kind of went off track from what we sold certain things to, like our funding agencies. But that's okay. They're generally very forgiving when they give us money at all. Okay. All right, so we're interested in massive stars. So things roughly 8 times the mass of the sun and up. And we're interested in their ends of lives. So at the end of their life, a star like this, and this is not to scale, basically looks like an onion, right? That stars sit there and they're burning lighter elements into heavier elements through nuclear fusion, and they burn them in sequence. And so at the center, they're burning heavier things than at the outskirts. And so at the outside, you have hydrogen, which is not doing anything. For most of the stars we're interested in, that hydrogen envelope is out towards Jupiter, right? It's Betelgeuse, basically, right? Betelgeuse is one of the few stars where you could actually take a picture of it and you get a bunch of pixels across it with the Hubble Space Telescope. It's actually more amazing. How many people know what the Gaia satellite is? So Gaia is this satellite which is trying to accurately measure distances. And so it can measure the position of Betelgeuse on the sky to like 10% of the size of the star, which is kind of an astonishing number. I mean, it helps that it extends out to Jupiter, but it's pretty amazing. Anyway, so you get the hydrogen envelope, which is way out, and then you're burning hydrogen to helium, helium to carbon, blah, 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 and then you get down to silicon, and you're burning silicon to iron, and in the last roughly day of the life of one of these stars, it will burn the mass of the sun from silicon into iron, and then you're stuck. Iron is the ashes of nuclear physics, right? Is if you go to higher things, you're doing fat man and little boy. You do fission and you blow things up by fissioning things. If you're on the low end, you do fusion, you get energy, and in the middle is iron where you don't get anything. So you build up this core of iron. It's building up to be about the mass of the sun, a little bit more, about the size of the Earth. And then it becomes unstable. It can't support itself. And the fundamental physics is that basically as the mass goes up and up, the fundamental speed at which the things are moving around approaches the speed of light. As they approach the speed of light, its ability to react against gravity gets weaker. The core becomes unstable and it will collapse. And so in some number of milliseconds, it will go from the size of the Earth to a proto-neutron star, which is sort of 100 kilometers per second across, and then it will bounce. Okay. The bounce sends a shock flying out, and that shock stalls. It comes to a grinding halt on scales of a few hundred kilometers per second. And then something has to happen. Either that shock somehow revives and goes blasting out through the rest of the star, or it doesn't. If it goes blasting out to the rest of the star, you get what's called a supernova. The star explodes, and you get a very bright transient. ASAS-SN, for example, can find 2 of those per day. The rate of supernova, if you could survey the entire universe, visible universe, is there are about 5 supernova per second. If you could survey the entire universe completely. It's not just this type of supernova, but anyway, we'll not worry about that. If the shock does not revive, okay, then it has to make a black hole. We have a fundamental problem, is that if I take my favorite star and I go to my favorite theorist, well, it doesn't have to be my favorite theorist, and say, dear kindest, sweetest theorist, can you tell me what will happen to this star? They'll give you an answer. You have no idea whether to trust them on it or not. That despite, well over 50 years of effort, exactly how and why the shock revives or does not revive is an open question. Okay? It's not true for all stars. The ones down around the bottom, the ones around 8, 9, 10, there the mechanism is understood. Those will robustly explode. And the mechanism is that the shock stalls, but the proto-neutron star is cooling off, and it is actually emitting all of its energy in these particles called neutrinos. Every cubic centimeter of your body presently has a neutrino in it. In your lifetime, one of those neutrinos might interact with you. But there is so much energy in those neutrinos that despite the fact that they don't want to interact very much, they can pump in enough energy to make the shock energize and blow up the star. The problem is what happens at higher masses. This also means you're talking about a minority of the stars, right? Because the number of stars as a function of mass drops very, very rapidly. And so most of these massive stars are the 8, 9, 10 solar masses. And so most of these stars explode, and the question is what happens to the rest. All right, so you get 2 possible outcomes. One is the thing we call the supernova. That's where the shock revives. The shock goes blasting through the rest of the star, and the star explodes, and that's what we call a supernova. And this will leave behind a neutron star. And an example is the supernova of 1054, which produces the Crab Nebula and contains the Crab Pulsar, which is a rapidly rotating magnetic neutron star. Option 2 is you get a failed supernova, and you get left behind with a black hole. And most, as I said, do this, and probably 10 or 30% are in this second category. Modern studies of this, while they have trouble saying what will happen to a particular star, can give you a map of whether a star is explodable. So which stars are easy to explode and which stars are not easy to explode. And it basically is we track down to some very complicated details about the final phases of burning carbon, and it has to do with the final density structure. Fundamentally, what's happening is you have this shock wave which is stalled trying to decide whether to explode the star or not. One of the things that is keeping it from doing that is that all the rest of the star is falling inwards. And if there is more stuff falling inwards, it is harder to explode than there's less stuff falling inwards. And so basically whether you can explode or not has to do with the details of just how much stuff is flying in to try to say don't explode as compared to otherwise. And so you could get these maps about here is the mass of the star when it was born, and here is the outcomes. So the blues are things which explode, the grays are things which don't explode. The height of the blues is how much energy they have when they explode. And you get this complicated landscape where stars around 15 solar masses are harder to explode. Stars in the low 20s can be hard to explode, and so forth. Except if I hand you someone else's setup for what the stars look like, the landscape changes. Okay? And whether they explode or not is based on models of whether they explode or not because we fully understand whether they will explode or not. In short, theorists in the absence of data are pretty useless. I actually started out as a theorist, and then I steadily switched to being an observer, so I'm allowed to be jaundiced. All right, empirically, we know some of them explode. In fact, we know most of them explode. And so this is the most famous local example, right? This is the only supernova in our galaxy that anyone has seen in the last century. It was actually the Large Magellanic Cloud. It's supernova 1987A in the LMC, and that star became that supernova.
If the thing went and formed a black hole, it would be obvious. It's basically neutrinos.
Okay. So the project we actually set out to do with the Large Binocular Telescope was to find the supernova which fail. Okay, so where they make a black hole without having an explosion. Okay. Because we realized it was the only way to do this, is that finding the stars which explode is pretty simple. They're bright, apparently, when they explode. But finding the ones which fail to make black holes is harder. You could try to find them from the neutrino emissions. So there were about 20 neutrinos seen from the explosion of 1987A. But if we had a supernova explosion in the galaxy today, detectors would see like 10,000 neutrinos. And if the thing went and formed a black hole, it would be pretty obvious. Is basically you'd have neutrinos, well, nothing. Right? The modern era of gravitational wave detectors, you could also see from the gravitational wave signal whether you formed a black hole or not. But both of these only have the sensitivity to do it in the galaxy. And so if you're looking for the formation of a black hole, you're talking about a project which will last a fair fraction of a millennium. My funding agencies have trouble covering me for more than 3 years. My lifetime also has some issues with that time scale.
2008.
And so if you want to find failed supernova, you have to do it on a larger scale. And what we realized is that you could just look for the stars to disappear. That basically we could go out, and with an 8-meter telescope, you can take pictures of the Whirlpool galaxy and look for red supergiants to go away. Doesn't matter what they do in between. Red supergiant, no red supergiant. Okay? And, you know, the galaxies we could look at have a supernova rate of about 1 per year. And so if the failure rate was, 10, 20, 30%, then we could find a failed supernova every 3 to 10 years. Being at Ohio State enabled this, because I don't think there was anywhere else which would tolerate that kind of time-scale project. Having tenure also helps. But we've been doing this since 2008. And we have one very good candidate, which is not the subject of the talk. But I'll show you another example of this, is we're going to show this sequence. So here is the first image we had. There's a star there. Okay. Ground-based data for looking at even these luminous stars in galaxies this is at NGC 6946, so it's 7 or 8 megaparsecs away. It's not the best way to look at individual stars. But we can look at changes. So here's the first image. Here's our last image. Even in the ground-based data, you can see someone's gone. But what we really use is a sort of magic of subtracting one image from the other image. And so here I've taken a whole bunch of images at very late times, combined them and subtracted them. And so here are images before what's going on. And now you can just see there's that one source. Why is there just that one source? It's because in general, stars aren't significantly variable. And so when I subtract the late image from the early image, all the garbage around it just subtracts away. And all I see is the star I'm looking at. Okay? And so here the star is gone. Okay? When I subtract it to where the star is there, I see the star, but all of the surrounding stuff goes away. Okay, so star, no star. Okay. Conveniently, Hubble Space Telescope also observed it. Here is a pre-image, and here's a post-image from the Hubble Space Telescope. Yes, it is substantially more impressive. On the other hand, your budget also, as discussed previously, just went up by a factor of a lot.
Understand the scientific method.
And in fact, we just got a HST image for it about a month ago, and it's still not there. Okay,
but that's not what we're talking about.
The refuge for trying to explain this, if you don't want this, is you make this star do something. You put a whole bunch of garbage around it. The garbage makes dust, so soot particles. Use the soot particles to absorb the light you can see. You re-radiate it out of the infrared where you can't see it. Okay. And the solution to that is apparently we have a new telescope called James Webb Space Telescope. James Webb can see far enough out in the infrared that you can kill that one. And so one of my amusements from January was rewriting the proposal to say is, gee, we should really look at this way out of the infrared to make sure it was a failed supernova, because last time they turned it down in part because it was so clear we were right that we shouldn't get the time. There's a certain part of understanding the scientific method to that response, which I had trouble with, but well, anyway, you're stuck. You just have to try again. Okay, but that's not what we're talking about tonight. So the other thing you could do to try to understand this mapping between exploding or not is to look at the stars which do explode. Okay, so you could look at, you see something explode, you can go back and try to look at the properties of the star which did explode. So you need some data from before the explosion, and you can go and say, okay, that's the star which exploded. And basically the game is if you can work out the luminosity of the star, that basically tells you the mass of the star at birth. We won't go into it, but we'll tell you the mass of the star at birth, but not the mass of the star at death, which is a kind of curious thing. And then, so you can basically try to work out, that mapping I had is here's the mass of the stars which exploded, here are the stars which don't explode, and then maybe you'll see that there's a gap. This is mostly done using archival Hubble data because Hubble's very high resolution eliminates the problem of that in a ground-based telescope. Even though I have no trouble collecting photons from most of these stars, I can't tell the photons from that star from the photons of the adjoining stars because of the blurring you get in a ground-based image. You then have the problem, though, that Hubble, looks at little tiny pinholes, and even Hubble can only do this on relatively nearby galaxies, which are big compared to the pinhole. And so it happens that you can get this data, but even after the entire lifetime of Hubble, there are only about 20 such cases where they have gotten information on the progenitor star, and there are 5 only kind of really good cases. What do I mean by that? Well, what I need is the luminosity. Okay. If I just go and look at the galaxy in a, shall we say, single filter, I get a flux in a single filter. Right? But to get the luminosity, I need to know the temperature. And unfortunately, someone brought this dust stuff into our lives, this absorption by soot. Okay? And so if I just have one band, I need to determine 3 numbers: luminosity, temperature, amount of absorption. Okay, I have some problems. 2 bands, still a measurement short. All right, so I need 3 bands to really have a handle on all 3 numbers. It's not very often that Hubble actually looked at a particular spot of the sky in 3 different filters. Usually at best you got 2. Okay? So that's why there are cases, but not very many good cases.
So we play the same game is that we could ask is, well, what are the properties of the progenitor star of the things which did explode? Because we just do the same thing.
So we don't have to worry too much about whether they got them all at the same time. It's just that you need, if you really want to constrain those 3 numbers, you really need to have looked at 3 different wavelengths. And it just doesn't happen. Two is not uncommon. 1 is most common. 3 is very rare. The thing which could really change that, which I'll mention at the end, is this Roman space telescope, which may be launched later this decade. I'll come back to that at the very end.
Here is, we've taken an
Okay.
average of images before.
So one of the things we sold or sell as part of this project to find failed supernovae is that obviously it also works for the successful supernovae. Star, no star. The fact that there was a supernova in between really doesn't matter. And so we could play the same game, is that we could ask is, well, what are the properties of the progenitor star of the things which did explode? Because we just do the same thing, right? In this case, I've done the opposite. But anyway, here is a real supernova. It is supernova, where to go? 2011 HD in the DH in the Whirlpool galaxy. Okay. And so here is our first image of that region. Here's our last image. Someone's gone away. And again, we can play the same game, except in this case, I've done the reverse. We were interested in whether the thing varied before it blew up. So here is, we've taken an average of images before the explosion and subtracted them from everything. So here we see nothing, because we've subtracted what was there before the explosion. And then as the supernova fades, we kind of get a negative image of the thing which exploded.
You build an average image of what you're looking at.
And this is what we sold, is that for anything that blew up in our galaxies, we could do this. We are doing our observations in 4 bands, UBVR. And so 4 bands, 4 is more than 3, so we could make high quality measurements because we have enough bands to measure temperature, extinction, and luminosity. And that works. By the way, I've cut out the supernova. A supernova in the Whirlpool galaxy is not the most brilliant thing to observe with an 8-meter telescope. It's a little bit saturated. But if we go back, M51 has a huge amount actually of HST data. And so we can actually directly
problem
compare
from the point of view
how
of
well
the
we can
story
measure the properties of the
is
progenitor,
that
to how well you could do it with
this
HST,
is the
and we
only
actually do as well as you could do with
one of
HST.
the actual
with this
supernovae
trait
which is
of
cooperative.
fraction. It's a little more sophisticated. What's really doing is
Now, there are
you build
about 10
an
other
average
supernovae.
image of what you're looking at,
And
and
not
then
a
for each
single
new
other
image, you
one
scale it,
has done this.
not just in the
That if you
transparency of
wait
the
a
atmosphere, but
long
also
time
the
and
shape
subtract,
of the images.
that you get that
So you
negative
can do a
image.
really clean job of
In
subtracting
general, we
everything
do
away.
this.
And the reason it
And
works
we
really
find,
cleanly is that,
basically, in this
yes,
scale,
there are a
there's
zillion
something that is
stars
still
near
white
it,
there,
but there are not a
meaning that there
zillion
is still
significant
emission
variable
brighter than the
stars.
progenitor.
So all of the stars which are not variable just vanish. And you're only left with
And so I won't show you this in
You're
images,
looking
but
at something which is
here are
very
some
variable.
examples. So these are now brightness. It's brightness or luminosity. That's luminosity relative to whatever we've put in the making the
Now.
average image. And so here's an example of another one where we've made the average out of the images before the supernova. Okay, and so basically 0, okay, is if something is as bright as the progenitor. And so if we see something coming out, like the previous case, what we want to see is on this side after the supernova, it should come down to be some negative number. And that negative number is the inverted image of the thing which exploded. Okay? So this is on scales of 10,000 times the luminosity of the sun. Okay? Still positive, still positive, still positive, still positive. And this is 3,000 days after the supernova. So I'm talking 10 years. Okay? This one we don't have pre-existing data. Okay, this is a supernova in 1993, famous one in M81, 1993J, and we can still see it, fading. Okay, so 0 just means is in whatever image we use for the average, that's 0. But we can still see it fading 30 years after the supernova.
So the time scale basically is too short, as we're seeing right now.
So on timescales of decades, these supernovae are basically all producing emission on the luminosity scale of the star which exploded. Okay. That was not what we sold. But, okay, well, science is a process. And so you now ask is, okay, where does that luminosity come from? Right? So you basically have 4 possibilities which we'll go through. So it can be emission produced by radioactive decay. It can be emission due to what are called dust echoes. I'll talk about each of these. It can be emission due to central engines, basically pulsars. Or it can be emission due to what are called circumstellar interactions. So if you take one of these dying massive stars, that luminosity at the peak is a combination of 2 things. It is not, none of the emission you see is due to the fact that you have heated this star to several million degrees Kelvin. So the actual heating of the star by the supernova is not what you observe as the supernova. Okay. Basically, it's the star is too small for you to see that. It basically just expands so fast that that energy just goes into expansion. The energy you see from supernovae comes either from radioactive decay or from simply that you have a big ball of ionized gas and you're going to reattach all of the electrons to their nuclei. It does not come from the fact you heated up the star several billion degrees Kelvin. It's a curious little fact. For the massive star explosions, most of the ones we talk about is the bulk of the energy is actually coming from just reattaching the electrons. And then some of it comes from radioactive decay. The other type of supernova, which are the exploding white dwarfs, it all comes from the radioactive decay. Why? It's because heat energy goes away when you expand. And so if I make you a big hot star,
it's super tiny. And so when it expands, all of the energy goes into expansion. And so I need a source of energy that survives going from a little tiny ball of gas to a big thing. And so I need something where the energy doesn't go away in terms of producing luminosity, going from something tiny to something big. And so that's the advantage of just hanging out the electrons not attached or waiting for radioactive decay, is that they don't care about the expansion very much. Okay? So radioactivity does certainly matter. The question is, can it matter at these late times? Okay, so we can talk about radioactivity. We actually understand the formation of elements in supernova reasonably well, and we can also just model them. So here is supernova 1987A. So this is its brightness, luminosity versus time. Okay, so this line is at 1,000 times the luminosity of the sun. 10,000 would be about here, 100,000, blah, blah, blah. Okay, and so here it's dropping. And so, you know, if we put in the luminosity of the progenitor of 87A, it's somewhere around here. And so 87A was fainter than its progenitor star after about 3 years. And if you ask where it's coming from, it's radioactive elements. The one that produces the big peak is nickel 56 going to cobalt, going to iron, with decay times of 77 days is the one that matters. And then you have nickel 57 to cobalt 57 to iron 57, blah, 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 blah. And basically what happens is the things with the most mass that decay fastest dominate early. And then as you wait later and later and later, it's the things which decay more slowly matter more and more. And so by the time you get out to sort of these time scales of here, it's 3,000 days, so 10 years, it's the decay of titanium. Okay, it doesn't actually make a lot of titanium, but you can see the number. Well, you may not be able to see them, but core collapse supernova make something under 1/10 of the mass of the sun in radioactive nickel. And that powers this phase, and then less and less. And so if I look at 87A today, the center of 87A today, its luminosity is actually significantly less than 100 times the mass of the sun. It's actually less than 10 times the, not mass of the sun, luminosity of the sun. And it basically has just followed this radioactive decay tail. We are trying to explain a signal up here on time scales out here. Okay, and so if you try to explain it with radioactivity, you have to produce 10, 100, 1,000 times as much radioactive materials as seen in 87A, and 87A is basically producing the amount of radioactive materials you expect. All right, so big X through this one. Dust echoes. Dust echoes are fun. They have almost no practical use, but they are really cool. So that is the dust echo from 1987A. One of the first cool things about dust echoes is they like to draw circles around the thing that produced them, even though the stuff producing the echo has absolutely no association with the thing that exploded. Right? It's just purely a pattern. And the game basically is, here's the supernova, and then you put a sheet. Right? Dust likes to be in these kind of thin sheets. The soot between the stars likes to be in relatively thin layers. And if you put it in a thin layer between, as the dust goes up, okay, the dust doesn't just absorb light, it scatters light. Scoop, scatters it into your telescope. Okay? It appears later than the actual peak because the peak just went straight to you. And this one took a diversion, and so the distance it had to travel is longer. And so the brightness of the dust echo is later than the brightness of the supernova because it took longer to get there. Yeah?
What kind of scattering is that? Ray scattering, B scattering?
A lot of it's just model as me scattering. Yeah. And so the fact that a bunch of these just says there are multiple sheets of dust producing the effect. And then with time, you see them expand. And so it's really kind of weird, cool, is you just get these expanding circles about the thing which exploded, produced by things which know absolutely nothing about the thing which exploded.
With a little trigonometry, couldn't you get a really good distance measurement to this original supernova?
So in this geometry, what you get is the distance between you get this distance. You don't get that distance. When we get to the next slide, I can tell you a little sub-story on that one.
And again, these are actually three-dimensional constructs. So what you're showing there is just basically just a.
Oh yeah, this is just a picture.
Yeah.
Yeah.
So these are actually, I mean, essentially bubbles, right? I mean,
Yeah. So the two issues is you have to think about whether you're going to look at it in what time you're looking at it. So in your time, as you see it, you see this.
Right.
The reason you will see the expansion is that it's kind of really illuminated something, right? Anyway, so that they're fun. And if you ask how bright they should be, it's basically is compared to the luminosity of the supernova. It depends on the fraction of the light you're going to scatter, right? If you don't scatter anything, you're not going to get anything. And then basically it kind of depends on how long supernovae are bright at the peak, which is about 3 months, compared to how long you've waited, which is kind of the time scale. So that you sort of expect is, this shouldn't really know how long you've waited. This definitely doesn't know how long you've waited. This definitely doesn't know how long you waited. That is how long you waited, and so you have a sort of prediction that they should tail off in a certain way on average. And they also have a prediction for what color they should be. Okay, that basically is you take the supernova light, you scatter it. Most cases, the dust likes to scatter blue light a little bit more than red light. So it should basically look like the supernova, but a little bit bluer. Anyway, this doesn't work. They're not fading the right way. The color is wrong, and you need too much dust. Now, come back to this one. The fun thing about dust echoes is you can see them a really long time later. So this in ASAS-SN, this thing here, extending across almost 3 degrees, that is a dust echo off of Tycho's supernova in 1572. These were previously discovered by someone else looking for them, but actually this is the most spectacular. They had a little patch like this, and we could see this really long. And so there's also a dust in the galaxy. There's also a dust echo seen from the CAS-A supernova, which is around 1670. Curiously, we don't actually know, because apparently no one really pinned down noticing the fact that CAS-A was a supernova in around 1670. But once you know the echo is there, you can actually take a spectrum of the light. And so we actually know that CAS-A was a type 2b supernova. Okay? This means that in the early phases it showed lines of hydrogen, and then the lines of hydrogen went away to leave only lines of helium. And in fact, we know, uniquely for CAS-A, that the spectra of a supernova depends on the direction in which you look at it. Because if you have a dust echo in a different direction, you get light from the supernova coming from a different direction. And the spectra of CAS-A from the different dust echoes look different, which means that if you were able to go for some other supernova and look at it from different directions, you wouldn't actually see the same spectrum. It's very niche-y, but it's super cool. There is none for the crab. The crab, if you actually look at the dust geometry, the problem is the dust geometry for trying to do this for the crab is wrong. The dust isn't conveniently traced. In addition to the 87A, there are a couple also seen in the LMC. And at early times, you can sometimes pick up images of these echoes with HST for supernova in other galaxies. Okay. But they're fun. Okay. All right, 2 down. 2 to go. Next one you can worry about is central engine, which is shorthand for basically pulsar spindown. So pulsar is a magnetized neutron star, rapidly rotating. If you take a magnetized neutron star and rapidly rotate it, it will be observed to slow down in its spin. That slowdown has to correspond to losing energy, and it's basically that if you take a kitchen magnet and spin it rapidly, it radiates electromagnetic energy. That energy has to come from somewhere, and the place it comes from is how fast the magnet spins. And so here's the Crab Nebula. Here is the pulsar at the center. This is a region powered by this spin-down energy. And for the crab spins around in 33 milliseconds, so basically 30 times a second. The time scale for that to double is about 1,000 years, close to the age. And if you ask what the energy is, it's about 100,000 times the luminosity of the sun. So that is definitely in the ballpark of explaining our phenomenology, except in these phases, they should be really lousy at producing optical emission. So the spin-down luminosity of the crab is 100,000 solar luminosities. The optical luminosity of this is a few solar luminosities. So you can produce a lot of energy and radiate it. It doesn't mean you're going to put it in the place where you're looking for it. That being said, we submitted this paper in December, and we just got the referee's report. The referee would like us to work more on this question. So it's a reasonable thing. Is we just basically said this, and the referee would like us to say more, it's fair. Okay. I would point out is you could start planning, right? Some of us have higher probabilities of being there for the millennium than others of us, but 2054, the millennium of the crab supernova.
How far away is it?
The crab. I am totally blanking right now.
It's not very clever.
It's like several thousand light years.
Yeah, it's something like that. Yep. It's an interesting problem is that actually most supernova remnants have horrible distance estimates. But you can do it for the crab now, particularly because of the Gaia satellite, because this is bright enough that you can actually try to get a direct parallax of the thing. That would be a separate discussion about how one might get better distances to supernovae.
6,500 plus or minus 1,600 light years.
Yeah, I think with Gaia it's better than that, but anyway. Which leaves us with the last option. I think that there really aren't other options, and that is what we call circumstellar interactions. Is that all stars produce winds. The sun's is rather unimpressive at the moment. The sun's present mass loss rate is about 1/trillionth of a solar mass per year. In short, it doesn't really matter at all. Well, except that it's going to end civilization. Well, how many people know about the Carrington event? Yeah. Right, so there was this event in the around 1850, in which a solar storm was so severe that basically things were sparking off of telegraph equipment. That basically, if you had a Carrington event now, it could basically blow out every major power transformer in the country, unless the utilities were prepared for it. Anyone want to vote for American Electric Power being prepared for this?
I don't think they recognize the term.
So yeah, it's basically the same thing when if you're a Cold War aficionado, there's this thing called electromagnetic pulses, is that you can cause significant damage to communications and electrical equipment if you set off a nuclear weapon up in the ionosphere, and it basically triggers a huge electromagnetic impulse, which then blows through the electrical systems and can. All right, last man standing is this guy. So these stars have winds, and if we're talking about red supergiants, which are the ones that produce the bulk of these supernovae, they have mass loss rates of around 1/1,000,000th of a solar mass per year. Okay, it doesn't sound super impressive until you multiply by 1,000,000 years, right? They're not the biggest mass losers. The biggest mass losers are the ones just a little bit below the mass of the stars that explode. They're called extreme asymptotic giant branch stars. They can peak out at 1/10,000th of a solar mass per year. They can basically black themselves out by dust forming in the dense wind. But you can ask, is what luminosity you get out of these things? And the luminosity you get, basically, it's the shock blowing through the wind and heating it up. And then you convert that, you convert basically kinetic energy of the shock into heat. If you convert it to heat, you could try to re-radiate it somewhere else. Okay? And the amount of energy you have to play with, it's proportional to the mass loss rate. It's proportional to how fast the shock is moving. That's the cube for what it's worth. And then it goes as inverse as the velocity of the wind. So the interesting thing is, first, is the luminosity you have to play with is independent of the distance, which means it's independent of time. So it can sustain the luminosity, in theory, in perpetuity. You have to worry about where the energy will come out. That's a slightly different question. But if you just have a normal stellar wind and you run a shock through it at constant velocity, the budget you have to play with is constant with time. It's just a question of where you're going to dump it out. It should be largest for the red supergiants. And I think I forgot to flag it, but all of the cases we see this, it was all but one of the things which would have been red supergiants, and not the one which would not have been a red supergiant. Okay? Those are the ones which have the highest mass loss rates. Good. The slowest wind velocities. Good. So we're seeing what we see from the things which should produce the biggest signal. Where the emission comes out is basically it comes out in emission lines of elements. And so basically the energy would come out in the optical in a bunch of emission by transitions of hydrogen and oxygen. Okay? And so it should have a peculiar color. Right? And if you go through the numbers and you put in a standard guess for sort of how much of this will actually come out in the optical, you would sort of say 10%. And if you put in the numbers, you get about what we're seeing. Right? Why is it a guess? The physics of going from this, which is relatively straightforward, to how much appears in emission lines in the optical is hard. Okay? It's one of those, there are calculations you look at and say, okay, this is super simple. And there are calculations where you go and say, I'd rather rip my heart out than do this calculation. It's a lot closer to that but it's also what you see is there are people who are stupid enough to do these calculations. And so here's an example of a prediction. So this is wavelength. Right? This is the red hydrogen H alpha line. And I think this is actually oxygen, not hydrogen beta. But the characteristic is you expect the emission to come out in a bunch of emission lines with very box shapes. And it's basically a box shape is what you get from basically a shell blowing out through something. And then here are some examples. Right? And you can sort of see it. And so, in fact, this guy and this guy are two of the ones we were talking about in the study we did. And so the spectra, where they're seen, makes sense. And we can also see it, we have only imaging, so we only have colors. But a prediction is it has a weird color that basically is if you go to U band and V band, B band in between is fainter, which is a super weird thing for anything other than something like this emission-like stuff. So it has a weird color, which only makes sense for emission lines. Okay, so that's all good. You can ask about 87A. 87A does have circumstellar emission. In fact, it has these iconic pictures. That is emission by circumstellar interaction. Okay, the peculiar geometry is driven by the fact that the wind has a peculiar geometry. The emission here is like 100 times lower than what we're talking about. Okay. The probable explanation is, let's go back to this. 87A's progenitor was strange. It was not a red supergiant, it was a blue supergiant. Right? Stellar wind velocities basically go with the escape speed from the star, which basically means is if you're a big puffy red star, they're slow. And if you're a compact hot blue star, they're high. So if nothing else, even if this number was the same, this number changed by a factor of 100. Yeah. And so it's not crazy that 87A would show this interaction, but it would be on a much lower scale than what we see for the things which have to be red supergiants when they blew up.
So that that supernova in 1987, correct?
Mm-hmm.
And so I'm looking at the fusion lines, and it passed several of the stars.
Yeah.
That's
Well, it's in projection, but the scale is approaching a light year. I mean, remember, the stars are just in projection in the large spectrum.
Like
Yeah.
foreground stars.
Yeah, they're not. They're probably not. They're not in the volume of. In fact, the brighter ones are probably all foreground. I've thought about this, and when I've tried to go through the numbers, I've determined, at least at the moment, it seems impossible about whether there are actually any stars behind this region that you could look at, and the numbers work out it's very unlikely. The reason that would be interesting is it would be interesting if you could look at a property of a star whose light is passing through this, but it just doesn't look like it works out. Yeah.
What are we looking at when we're looking at these rings? What am I observing?
Oh, so the picture of this thing is that the actual wind geometry is kind of like an hourglass. So this is where the supernova is sort of running into kind of the narrow bit of the hourglass. This is actually a radiation effect of where the radiation from the supernova is hitting something further out. That makes sense? Right, because this, right, the actual shock can only happen on the speed the shock goes out, but the effects of the radiation go out at the speed of light. And so you could have two zones where the supernova is affecting things, one where the physical stuff has moved, and one where the radiation has reached. And so then it's the property of the morphology of the wind is believed to be this kind of hourglass-shaped thing. And then so if you imagine cutting a sphere moving at the speed of light with an hourglass, you get a ring. And if you imagine a sphere of the supernova going out, cutting the hourglass, you get a ring. That make sense?
Yeah, and if I remember recently, they're starting to see the actual fireball of the remnants. Recent Hubble image.
Yeah, I don't remember. I mean, this one is quite early because you can still see something at the center. So there's not much emission at the center these days. So a little bit of sociology for you. So we put this paper out in December, basically saying is this emission by circumstellar material appears to be ubiquitous, and it's this explanation. So a month later, a theory paper comes out saying, we predict that this emission should be ubiquitous. Their only mention of the paper, which had been available to them for a month, was this quote. And, you know, it is one thing that always makes your job interesting is the people. Anyway. All right, so where could you think about going? So one thing we did is what we did was we really looked to the supernova of these galaxies going back to 1980. There are some number going back to the earliest is I think like 1913. And so Michael is going back and seeing if we see anything from the still older supernovae. There aren't as many of them just because people were looking. The tea leaves is we're not seeing them. And that doesn't seem crazy because for the numbers for the ones we do see is mostly they're on the verge of fading below where we can see them. That a lot of them actually are approaching the point where we should be able to start seeing the inverse of the image of the progenitor, just much, much later than we had advertised. The sample should start to grow significantly. There's the Rubin telescope in the south, which is basically a 6-meter telescope designed to do time domain. It doesn't massively expand things. Basically, it's only going to pick up the galaxies we can't do. And it just turns out because of the distributions of galaxies, we're doing most of them. Most of the galaxies of interest are visible from us, and so they're going to add like 1/3 more, not twice. The one which can really make a difference is there's a telescope which is supposed to be launched later this decade. It's basically a Hubble mirror. It is literally a Hubble mirror. A certain unnamed agency called up and said, "Would you like a 2.5-meter telescope?" And so the reason the Hubble is a 2.5-meter telescope is that's what the unnamed agency was making. But it will have a much, much bigger field of view camera, one comparable to what we're doing from the ground. And so it can just bang out this sort of data. And then the resolution of a Hubble, which is basically what it has, you can do this at much higher distances than we can do it. So it can do a bunch of things. Okay. So in theory, it is one will be able to do a real survey of what these stars are doing in terms of their mass loss just prior. That's sort of interesting. Okay, any questions on this? All right, do you want an appendix? All right, it's totally unrelated. All right, how many people have measured a magnitude? All right, so you go and take your picture, and you want to convert it into the brightness of your star. So you have a detector. Your detector collects a certain number of counts. Yeah. And the way it works for mostly is most of the astronomical ones are still CCDs. The CMOS are different. They're somewhat different in their physics.
Yeah.
But basically, the way the CCD on a camera works is it has a well, it collects electrons, okay, and then you count the electrons. The well can only hold so many electrons, okay? And so the question is, what happens to the electrons when you've got more of them than you can deal with? They like to ooze. And so basically is if you take a picture of a star which is producing too many electrons, you get a trail of the image basically along the read direction of your detector. So you have a bright star, and then you have a trail. And so basically is we all pretty much give up on trying to do what is the brightness of a saturated star because we don't know how to do the accounting for the, okay? And so that means generally when you're taking an astronomical image is because of however long you integrate, you can measure the brightness of things from the brightest things which are not saturating to the faintest things where you just run out of counts. So a curiosity we've always had in our ASAS-SN survey is could we figure out a way to do the brightness of the things which are too bright? Right? If you go out and ask for a light curve of Betelgeuse, you can't get one. Betelgeuse is first magnitude. Okay? We're using these 14-centimeter telephoto lenses. Betelgeuse is 10,000 times brighter than the limit where we start to have this problem of saturation. Right? And we're not even trying. Right? But so it basically means is there is no source of all sky information on the brightness of things. We don't have to go, we can stay fainter than what the eye can see, 6th notionally, 4th in Columbus. to where Assassin starts to have problems is at 12th magnitude. So, okay. So the information is presumably all there. We just don't know how to get it. All right. So have anyone heard of anything recently which is good at figuring out information that is there when you don't know what it is? Yes. Convolutional neural networks. So this is just an experiment we've tried. We've only been trying it for 2 weeks, but it's just sort of so weird. It's kind of weird. All right. So I've already done this. So this is just an experiment. All right. So for those of you who are in magnitudes, space, right, this is 5th magnitude. So in theory, your eye is dying here. All right. But go from here to here, that's 100 times fainter. That's 10 to the 4 times fainter. Our notional saturation point is around here. So brighter than that, conventional ways of measuring the brightness of stars fail. This is an experiment using a convolutional neural network. So we've used Gaia to estimate the brightness of the star. And then we used a convolutional network to compute the brightness of the star from a little postage stamp of assassin data. Basically 21 by 21 pixels on the star. It doesn't know anything. It knows absolutely nothing about astronomy. It knows absolutely nothing about computing the brightness of stars. And all it knows is I have a 21 by 21 postage stamp image, and I'm supposed to get this number. That's all it knows. It basically produces the right answer, running several thousand times brighter than any conventional way of doing the brightness would work.
I'm curious, what kind of computer do you use to do that?
It's my desktop.
Yeah.
It's not actually that time intensive. It's just kind of,
So I can do it at home?
you could do it at home. I mean,
I work with neural
we probably have a better training set than you do, given that I have 6 million images in hand. Right. Well, this is the dots on here. They're 10,000, sort of randomly they're randomly selected. The black points are the ones it's trained on, so in theory that's a little bit unfair. But the red ones are the ones it didn't know anything about. There's not much difference.
That's impressive.
It's just kind of.
Yeah.
So would this work for doing very star work?
Well, that's the question. So this is asking a slightly different question, and so we need to get to that question, because this is asking sort of, for the light curve, this could be wrong by a small amount, but for the light curve, all I need it to be is always wrong the same way. And that I don't know the answer to. If it's wrong jumping up and down, then this is a problem. And anyway, that's sort of we haven't gotten there yet. But it was just kind of such a weird, semi-technical thing that I thought I'd overshare it with you.
So you said training, so you're giving it some stars where we know the magnitude and telling it?
Yeah, so in this case, it has about 7,500 stars where it has the postage stamps, and I've told it what the number it should get is, which are gotten from this Gaia satellite. Well, because in this regime, right, I have this same problem, is they're so bright, where am I going to get the information for what the number I'm supposed to give it is? And it turns out the Gaia satellite can do.
The training is basically what you do when you actually measure magnitudes manually, right? I mean, except that you're actually doing it.
Aperture photometry is a pretty well specified thing,
Yes.
right? Is you measure the counts in here, you measure the counts in the sky, you subtract it.
And-
Right? It's a well specified thing.
Right.
Right? If you try to do that for these guys, I could tell you it doesn't work.
Right, it doesn't. It doesn't basically, because you're basically saturated at that point. So you don't know.
Yeah.
That's basically
Yeah.
it's unknown. But the method that you use to actually teach it if you will. It's basically a simple method.
I have no idea where it's getting the information from. It's the mystery of the convolutional neural network. It is figuring it out.
It's figuring it out.
Our robot overlords are approaching.
So this seems to be most useful from about 7th to about 12th magnitude, because beyond that, assassin is good for the magnitudes. And then lower than that, it looks like you've got a lot more.
Well, there's some, anyway, there are various issues at the right end because of the way I built the
They're too bright to
They're
train.
just too bright.
No, it's also is just the way I sampled. It's not really weighting the training that well down there.
Okay.
But anyway, I don't know. It may well die.
Maybe the really bright ones are bigger than 21 by 21 or something.
Yeah, there's probably a limit how far you can push it, but it's just kind of.
Very
I mean, literally, this was like a few days' effort, and it's like.
Yeah. You could do it with like amateur photos, just thousands and thousands of amateur photos.
I don't have to because I already have 6 million images.
Yeah,
But
data.
Yeah, you have a lot of assessing data
Okay.
anyways.
all right. Any final questions? Yes,
Can you answer questions about neutrinos that I've had for a while?
I can try.
What's the difference between a low energy and a high energy neutrino? The sun's neutrinos are low energy and the supernovae are high energy?
Okay, so we're usually in the professional lingo. That's not the division. Okay, so the sun's neutrinos are coming from various nuclear reactions, and they have energies of order mega electron volt. The ones from supernovae also have that kind of energy. There could be a little bit more. But they are mostly just the fact that you have a hot neutron star, and they are not due to specific nuclear reactions. So in origin, they are different, but the energies are kind of the same. High energy neutrinos, they're talking about things which are way up there, like, gazillions of electron volts. And those are associated more with phenomena such as cosmic rays. And so many of the things which would generate the very high energy cosmic rays are likely to also generate high energy neutrinos. And so when people talk about high energy neutrinos, they're usually talking about the ones associated with whatever is producing cosmic rays. And those are giga electron volts, trillion electron volts, more like the things you're doing in a high energy collider.
What's the difference between the neutrinos? They do have mass, we know now,
Mm-hmm.
and they have velocity. I guess they don't travel at the speed of light then?
Yeah, but in general is all of the ones we can detect are moving epsilon less than the speed of light, right? Because they have masses of like 1/10 of an electron volt. You're talking, for the ones we're talking about, they have minimum energies of 1 million electron volts, and so those guys are moving just under.
Close.
Yeah. So the one neutrinos which have kind of luminal level velocities are the neutrinos associated with the Big Bang. Right? So those have a temperature close to the temperature of the Big Bang. Those are no longer moving, those are cold enough that they don't have velocities close to the speed of light. We also have absolutely no idea about how to detect them.
So what gives them the difference in energy?
For which?
Well, the different neutrinos, the finer.
Different origins. I mean, the ones from the Big Bang.
They're not the same kind of particles then?
Yeah.
No, they're the same particles, just different production mechanisms.
Different speeds.
It's the
Different. So the ones.
99.99999.
Yeah, so the ones.
1/2 mv squared sort of thing?
Hmm?
Is it 1/2 mv squared sort of thing for the energy?
No, you can't do that with relativistic.
Yeah,
Because you have
but-
to take relativity into account.
But it's you've sort of got.
Speed of light, the one that's-
It's just they're the same particles, but you have a whole bunch of different production mechanisms. So the Big Bang produces things which today are very cold. Nuclear reactions of the sun produces ones which have the characteristic energies of nuclear reactions. supernova produce neutrinos with the characteristic energy of the temperature of the proto-neutron star. It happens that that energy is kind of the same as the other energy. And then the ones associated with cosmic rays have the energies of whatever is producing the cosmic rays, which is very much higher.
Do they come from subatomic particles, quarks, or?
The origin, it's it's a lot of nuclear reactions just produce neutrinos as part of the rules of doing nuclear reactions. The neutron stars just produce them because they're hot. The Big Bang also, they're just produced because the Big Bang was hot, but today it's so long ago that it's cold.
Things that are hot generate photons.
Yeah, but so if you're hot enough, you'll produce equal numbers of photons and neutrinos.
Under the photons and the neutrinos, can you detect the difference in arrival time?
So people try that. This is one of the tests of essentially, what's the so-called equivalence principle, is could you see a difference between the arrival times? But there would be a difference because the neutrinos have a mass and the photons don't, but nothing gives you that time precision to really see that. It's a pretty small effect because the mass of the neutrinos are so low and the energies where they're produced is so high. For the ones where I could do this test, it's not really feasible. Anyone else?
I'm asking the astrophysicist.
Sure.
Are there an equal number of protons and electrons in the universe?
As far as we can tell, the universe is neutral. So that the number of plus charges and minus charges is the same to very high precision. There are reasons there are reasons in particle physics for why that ought to be or is very likely to be. But you can write down something where that might not be true. Just to the extent it's not true, then it has to be a very small effect. Just because electromagnetism is such a strong force. But as far as we can tell, is the universe is neutral.
But it is regular matter as opposed to antimatter, basically.
Yeah, well, charge, so as far as we can tell, there's not much antimatter drifting around either. But that's a different question, right? Charge is a different question from matter versus antimatter. But yeah, so now, why we have this imbalance between matter and antimatter, we do not have a good theory for. So we know of effects which will produce such an asymmetry. You can see them in particle accelerators, but none of the ones we have seen are big enough. Okay. If you take the universe, you go to a high enough temperature, where basically everything is in equilibrium, right? You have equal amounts of matter and antimatter. Okay, and so you need something which will produce a slight asymmetry. And then when the universe cools down, everything tries to annihilate and you're left over with a small asymmetry. Okay? So the question is, what generates that small asymmetry? And that we do not have a tested idea for.
So, getting back to the subject at hand, you mentioned that you were a former theoretician, but now you're a little bit more empirically driven. You've just gone through a large number of things that probably don't add up to these supernova remnants that kind of hang on for quite a bit longer than expected. All the different things that we can account, all the different ideas that we can throw out there to try to account for the brightness not dropping as fast as you expect it to drop. Ask you to put on your theoretician hat now that you're getting a lot more data here. you got any ideas? You know, what?
Oh, I think our explanation is correct.
Okay, so
Yeah.
you think that this is enough to account for it?
I think that the numbers just work out pretty well, is that if you just take the normal winds of stars and the expected properties of the supernova shock and a not crazy assumption for how much you get converted into what you'll see, it all holds together.
So you're hopeful, but you're also hopeful that it's not so much of a slam dunk case that they're going to basically tell you that it's so much of a slam dunk case that doesn't bother the observing time.
Oh, anyway, that one was a different special case. So here we'll just, it will just happen as the observations be done. There was a particular case. It was, there was a question of observing an object.
Okay.
The exactly one known object is present to test a particular theory. And they didn't want to give 1.6 hours of time to confirm the formation of a black hole, which kind of boggled my mind. But anyway, the proposal is back in. We'll see. This one is more. This is not a. This is a pretty straightforward thing. And because you have a lot of these existing these other existing spectra where for some other systems you see these boxy emission lines, that eliminates the nuclear decays and the dust echoes, just because they can't produce that kind of spectra, and then we see the colors. The Pulsar Spindown would also produce such an emission line spectrum. So I guess the referee has a fair point, but we should.
On a similar note, you showed the graph of whether or not the star is going to actually produce a bright supernova or will put out of existence when it collapses into a black hole. That doesn't seem to be, it's not a particularly linear effect. I mean, there's little gaps and it's very chaotic
yeah, so people have explored why that is. And it basically has to do with a lot of devilish details in how the stars do carbon burning. And that the carbon burning at the late phases can happen in regions where the energy is carried either by convection, so fluid motion, or radiation, so radiation. And the exact core structure, which will then determine the explodability, depends on exactly what it is doing in those regimes. And it turns out that their behavior in that carbon burning and which regimes is basically almost chaotic in the theoretical studies. And so that leads to this very complicated landscape of this guy explodes, that guy doesn't explode.
I mean, just as, it would seem to me that you get something bright after the black hole is formed, because you get a accretion disk or something like that from all the material that was around the star, or at least the outer atmosphere of the star, and the core collapses down to a black hole, starts to fall in, forms an accretion disk. Why don't you get this little mini quasar for a while?
That is an issue. What you expect is that so you do expect sublate type accretion. You expect it to tail off basically as a power law. Exactly what you expect to see is more messy because I can sort of predict the feeding on kind of big scales, but I don't really understand the physics of the feeding on small scales, so we'll get modified. So if you go, and we go and do, say, these JWST observations, and we see a source, then we will have to deal with the question of whether it is a surviving star or late-time accretion. Okay? The one thing to be sure of is that JWST is going to last for 20 years, and if I go and look over those 20 years, I can tell you which. So it's because the one is basically not time dependent, and the other has to be time dependent. So it's a legitimate worry, which you know.
Can you predict if Betelgeuse will be a black hole or really? Is there enough data to predict that at all?
So the curious thing is there are arguments about what the mass of Betelgeuse at birth was. And so some make it relatively lower mass, in which case it definitely would explode. And some put it in this range where things become ambiguous. So the answer is, I don't know. It actually is in this area where it has this issue that we don't know the distance to Betelgeuse perfectly. It's actually, turns out, we have this fancy new satellite for measuring distances, except Betelgeuse is too bright.
It's too bright, you can't tell how far it's away?
It's for the Gaia satellite, Gaia does not measure the parallax of Betelgeuse. It's too bright.
You take a shorter exposure.
Zero, 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 zero.
You know, it does have the advantage, if Betelgeuse goes, you know, the outcome will be unambiguous. Right? You know, even if you don't worry about gravitational waves, as if Betelgeuse goes, some of the neutrino detectors will be picking up 30, 40, 50,000 neutrinos from the core collapse. And if it makes a black hole, it would be totally unambiguous that it made a black hole. So we will know the answer. The curious is we don't fully know the answer for 87A as to what the outcome was. There's a recent paper claiming or arguing for detection of a neutron star, but I found it fairly weak. So we don't actually know what 87A produced.
I have one neutron star question. If they're mostly neutrons, how do they have a magnetic field?
They're residual electrons, or they're residual protons.
There are electrons.
It's not exactly all neutrons. So in some models, in fact, their interiors are actually superconductors. So not only are they good conductors, but they're perfect conductors of their interiors. But in any case, and then as you go to the surface, right, they become more and more normal stuff. So the crust is like crystalline iron. All, you know, the crust of the neutron star is like that. Of course, it, you know, weighs more than the Earth.
There are
Right.
live electrons that spin around, and that's where the magnetic field comes from.
So it doesn't go perfectly to neutrons. It's just,
Protons don't count.
well, you just need to have the charged particles and their ability to move around. So there is the question of the time scales on which the magnetic fields decay or don't decay. So there is evidence that if you have a neutron star, which is accreting stuff, that the dumping of stuff on the surface starts to, the usual phrase used is bury the magnetic field, and it starts to suppress the.
One last question, let's move over to the next one, a black hole.
Well, why do we let people who want to leave, and you can come up and
Thank you very much.
About the size of the black hole.
come on down.